Introduction. EMG signals are electrical signals generated by activation of skeletal muscle due to neuromuscle activities. These signals arise from the electrical potentials produced by motor units when muscle contract, making EMG an essential tool for studying muscle function and behavior. EMG signals are typically measured using electrode placed on skin surface or inserted into muscle tissue. The physiological relevance of EMG signals includes that they can be used to diagnose disease such as motor neuron disorder. While electric analysis can indicate the onset of fatigue during physical activity, EMG help to understand motor control mechanism and how they change as a result of injury or disease. The application of use in biomedical engineering, including chemical diagnosis and human-machine interface. Waylight transform is for analyzing EMG signals due to ability to capture transient and non-stationary features. It decomposes the signals into multiple scalars frequency band using white light function, allowing detailed analyzing of signals characteristic and different resolutions. Time frequency analysis. EMG signals are non-stationary and complex time-dependent characteristic due to the dynamic nature of muscle contraction. Time frequency analysis methods are essential for meaningful features from EMG signals, as they allow the examination of signals components in both time and frequency domains.
I will now explain regarding the data acquisition process, focusing on the dataset and its key characteristics. The dataset used for this study is titled EMG Gesture Recognition Dataset and was sourced from Kaggle. It is specifically designed for analyzing muscle activity to recognize different hand gestures. The signals were captured at a sampling rate of 200 Hz, meaning 200 data points were recorded every second for each sensor. This ensures high temporal resolution, allowing us to track subtle changes in muscle activity over time. Each recording lasted for 20 seconds and 6 recordings were conducted per gesture, resulting in total duration of 120 seconds of data for each gesture class. The dataset consists of 8 channels representing signals from 8 EMG sensors placed on the muscles. In terms of data structure, each CSV file contains 64 columns representing 8 sensor channels with 8 readings recorded per timestamp. In each line in the dataset corresponds to 40 milliseconds of recordings. The dataset includes 4 distinct gesture classes: Class 0, Rock; Class 1, Scissors; Class 2, Pepper; and Class 3, OK, which index finger touching the thumb with other fingers spread. For my analysis, I focused on the Scissor gesture, which is Class 1. This gesture involves a specific muscles activation, making it an excellent choice for studying EMG signal patterns. In terms of recording method, each gesture was prepared and held steadily during the recording process to minimize noise and variability. The recordings were stopped while the gesture was still being held to ensure consistent data capture. Finally, considering the sampling rate, duration, and the number of channels, the total number of data points collected for each gesture is substantial, providing a robust basis for signal processing and analysis. With this understanding of the dataset and acquisition process, let's move on to the techniques we use to analyze the EMG signals. We use 2 advanced signal processing techniques, which are short-time Fourier transform (STFT) and continuous wavelet transform (CWT). The STFT divides the signal into short overlapping segments using a Hamming window of 256 samples with a 50% overlap. A 1024 point FFT is applied to each segment, enabling us to observe how the frequency components of the signal vary over time. For a more flexible time frequency analysis, we applied the continuous wavelet transform or CWT. Using the modeled wavelet and a scale range from 1 to to 128, CWT allowed us to capture subtle variations in the frequency dynamics of the EMG signals. Both methods have their unique strength. The strength of STFT is STFT provides fixed resolution in time and frequency, while CWT adapts to the signal.
Next, we start with the EMG signal processing. First, we take the raw EMG signals. So for the code, the script begin by loading the EMG data that we have select from the Kaggle, and then we select channel 1 for the processing, as channel 1 is the most related for our data, and then we remove the DC offset, which is the baseline drift, by subtracting the mean of the signals. This will center the signals around 0, preparing it for the further analysis. Hence, the graph that we get is the raw EMG signals from channel 1 over 15 seconds, and this graph contains noises and baseline fluctuation, which are typical in unprocessed EMG data. Next, we filter the EMG signals. In the code, a bandpass filter with 20 Hz, low and 99 Hz high is applied to remove any unwanted noises. The low frequency noises, such as baseline drift and high frequency interference like power line noise, are filtered out. This step is to ensure that only the frequency relevant to the muscle activity are retained. Hence, the graph that we get is this show the filter EMG signals. So compare this to the raw signal, it is much cleaner and better as it represents the actual muscles activity. In the next step, we rectify the EMG signals. So indicate in the code, the ABS function rectifies the signals. So this approach smooths the signals while preserving the key activity trends. So the filter signals is rectified by converting all the negative value into positive value. So in the graph, we get the rectified EMG signals. So this step ensures that all variation in the signals are positive, making the data easier to interpret. So in the last graph, which are the EMG envelope, so to extract the EMG envelope, the rectified signal is moved using a moving average filter with a window size of 100. So this step highlights the overall trend of the muscles activity. It removes rapid fluctuation while also preserving the key features of the signals. So this script uses subplot to plot all the stage of the signals processing. We put titles, access labels, and also grid to enhance the clarity of the signals. So the fourth graph shows the EMG envelope. It provides a clear and concise representation of the muscle activity over time, which is ideal for gesture recognition. So this demonstrates how the EMG data undergo several processing steps to produce important signals, and these steps are crucial for identifying gesture such as seizure in our case here.
Script used for computing the STFT of the filtered EMG signal. The code follows this step, which is the first one is define the parameters, which is the segment length, overlap percentage, and also the FFT points. The second part is compute STFT, which the spectrogram function is used to generate the time frequency representations. And the third one is visualization. The spectrogram is plot showing frequency on the y-axis and time on the x-axis and the power in color. And then this will show the result in this. This code is allow us to visualize the changing frequency components of the EMG signal over time, helping in better analysis. This is the spectrogram generated from our analysis. It represents how the frequency content of the EMG signal evolve over time. The x-axis shows time, the y-axis shows frequency in Hz, and the color scale represent the signal power in decibel. So from this visualization, we can observe that most of the energy is concentrated in the lower frequency range, which is common for EMG signals. The variations in intensity indicate changes in muscle activation. In this part, we analyze the EMG signal using the continuous wavelet transform. Unlike the short-time Fourier transform, which use fixed time and frequency resolution, CWT, which is continuous wavelet transform, provide better time frequency localization, especially for non-stationary signals. So this is the MATLAB script used for CWT analysis, which has three things, the main things. The first one is compute CWT, which the CWT function extract wavelet coefficients across different frequencies. And then the second one, plot the result. The coefficients are displayed as scaleograms showing how frequency content evolve over time. And the last one is logarithmic scaling. The frequency axis is set to a logarithmic scale for better visualizations. This is the script. This allows to capture transient changes in the EMG signal with high resolution. Next to it is the scaleogram obtained from the CWT analysis. The x-axis represents time, the y-axis represents frequency in hertz, which is logarithmic scale, and the color scale indicate the magnitude of wavelet coefficients. So what we can observe is that most of the energy is concentrated at the lower frequencies with some transient high frequency activity at the beginning. This confirms that the EMG signal has dominant low frequency components which are crucial for muscle activity.
Hello, my name is Nuruda. So I will be presenting the analysis of two signal processing technique, short time Fourier transform and continuous wavelet transform. So we will explore how the technique help analyze frequency and time information in a given signal and highlighting their respective features and observation. So let's begin with a short time Fourier transform. On the y-axis, we have frequency, while the x-axis representing time. So each point of the graph corresponds to a specific frequency at a specific time in the signal. So next we interpret the color representation in short time Fourier transform plot. For the strong peak, bright color at certain time interval indicate that the frequency is dominant with a high amplitude during those time. Like the yellow one is the brighter color and the blue one is the darker color. So the bright color on the yellow color is the strong peak of the signal. And then if a bright color persists over multiple time frame, it suggests that the frequency is stable and consistently present throughout the signal. So the general observation from this short time Fourier transform plot, we can see distinct frequency band that evolve over time. In particular, lower frequency below 20 Hz are prominent with a focus on the 10 to 15 Hz range. So there's also activity in uh, above 20 Hz, but it is not as consistent or strong as the lower frequency. So looking at the time variant in the short time Fourier transform plot, the lower frequency bands exhibit high activity in the initial portion of the signal. As time progresses, there's a shift towards higher frequency activity. So this suggests a change in the signal characteristic as time progresses. Now let's move on to the continuous wavelet transform. Like a short time Fourier transform, the y-axis represent frequency and the x-axis represent time. However, in the continuous wavelet transform, smaller scale correspond to higher frequency and larger scale correspond to lower frequency. So in terms of color interpretation, high amplitude, bright color at specific time and frequency indicate that the signal has strong presence at those points. So if we observe sharp and bright peaks at different scale, it may suggest transient feature or sudden changes in the signal at those specific time and frequency. The general observation from the continuous wavelet transform plot, the signal is predominantly below 10 Hz, which some potential activity in the 10 to 20 Hz range, though it's weaker. The plot shows a consistent pattern of activity across the time frequency plane. So regarding the time variant, we observe a gradual increase in power within the higher frequency in range 10 to 20 Hz as time progresses. This suggests that there is a shift in muscle activity or signal characteristic over time, especially toward higher frequencies. So to summarize, that short time for transform plot show strong low show, show strong low frequency activity initially, shifting towards higher frequency over time. And the continuous wavelet transform plot reveals the dominance of lower frequency with a gradual increase in higher frequency activity as time progresses. So both methods provide unique insight into the how the signal evolve over time, but with slightly different frequency representation. Next, I will be presenting a comparative analysis of two advanced signal processing techniques, the short time Fourier transform and continuous wavelet transform. These methods are commonly used to analyze signal like EMG. So starting with short time Fourier transform, its main strength lies in its ability to provide clear spectrograms for dominant frequency. It performs well with a stationary signal where frequency components are stable. However, its time resolution is limited by a fixed window size, and short time Fourier transform is computationally efficient and faster, making it great choice for quick analysis of simple signal. So next, let's look at the continuous wavelet transform. So it excels in handling non-stationary signal and transient event thanks to the adaptive resolution. So continuous wavelet transform provides superior detail for high frequency and short life event. It rich timescale representation enables multi-scale analysis, making it highly effective for analyzing complex and dynamic signal. Okay, while short time Fourier transform is simple and efficient, it has its limitations. The fixed trade-off between time and frequency resolution cannot be optimized simultaneously. Additionally, short time Fourier transform is sensitive to noise, especially in high frequency region, and relies heavily on the choice of the window. On the other hand, continuous wavelet transform can be computationally intensive, requiring more resources than short time Fourier transform. Its results are heavily dependent on the wavelet chosen, and interpreting its detailed outputs can be challenging for beginners. Noise can sometimes obscure weaker features, though the choice of wavelet can help mitigate this. So, in terms of application, short time Fourier transform is most effective for stationary signal, such as basic EMG frequency stability. Meanwhile, a continuous wavelet transform is ideal for non-stationary signal that contain transients or varying patterns, such as EMG bursts. So STFT provide consistent time and frequency resolution, making it best for stable signal, while continuous wavelet transform, additive resolution, and ability to detect transient make it the go-to method for complex and non-stationary signal. So in conclusion, this study demonstrates how the short time Fourier transform and continuous wavelet transform methods provide complementary insights into time frequency characteristics of signals, while the short time Fourier transform reveal more about frequency shift over time with clear distinction between lower and higher frequencies. The continuous wavelet transform offers a final view of signal variation, highlighting both steady and transient activity. The findings suggest that the signal's characteristics evolve over time, particularly in increasing activity in higher frequency. This insight could be useful for applications like signal analysis, muscle activity monitoring, or time series analysis in dynamic system. So in future study, refining the frequency band of interest or exploring more advanced signal processing techniques could provide even clearer insights into the evolving nature of these signals. That's all from us. Thank you.